Okay, in this video, we're going to be talking about horizontal asymptotes as they pertain to these rational functions that we're going to be talking about. So, how do horizontal asymptotes happen? Well, in essence, horizontal asymptotes happen, and it's this simple idea. It says, as x approaches infinity, y is going to approach a number. Or as x approaches negative infinity, y is going to approach a number again. So this is sort of just flipped around from our vertical asymptotes that we talked about in the vertical asymptote video. Right? That one, the y was getting really, really big or really, really small, and x was getting close to a number. This is the opposite. So how do we find these vertical asymptotes, or these horizontal asymptotes, excuse me, we're talking about horizontal in this one. Horizontal asymptotes, how do we find them? Well, what we want to do here is basically pretend that we could put, infinity in for x. So, of course, we can't put infinity in for x because infinity isn't really a number. But you can think about them as the biggest number you can imagine. So there's two ways you can think about it. You can think about it as actually maybe using this symbol to mean a really, really big number or a really, really teeny tiny number. Or you can just pick a really, really big number, a really, really small number, and see what's happening. I'm going to kind of use this symbol, but I don't want you to get upset because later on, actually, you cannot use infinity as a number. But we're using infinity as the idea of a really, really huge number. Or let's say b. We'll say b is equal to a really big number, the biggest you can think of. Okay, and we'll maybe use some actual numbers so you can see, but let's say b is a really, really big number, okay? So I'm going to plug in a really, really big number, a number that's close to infinity. That's what b is going to be. You with me? B is the biggest number I can imagine in my brain. So don't say 10 or 100. This is, a billion, jillion, cajillion, trillion, million, right? A really, really big number. Okay, so let's think about this. So let's put it in for x, right? So as x gets really close to this number, the biggest number I can imagine, the number that's real close to infinity, what's happening to this fraction, right? This is a fraction with a really big denominator, right? This is a fraction with a really, really big number on the bottom. So what happens? Think about it. If you start putting bigger numbers on the bottom of the fraction, what happens to the value of the fraction? The value of the fraction starts to go down, right? If I start putting these bigger and bigger numbers on the bottom, the value of the fraction goes down. So as x is approaching infinity, right? As I keep putting these huger numbers into the bottom, y is actually getting really small, close to what number? 0. Do you see that? As x gets really big, these fractions get close to 0 because that's what this fraction is equal to, right? It's equal to the y value. Does everyone see that? So this fraction, as I put these big values in for x, the y is getting close to 0. This is creating a horizontal asymptote. And my horizontal asymptote is that line. And so the line is y is equal to 0. The other thing we can think about is, let's say that I put a really, really tiny number. So let's say that negative b is really close to negative infinity. Okay, let's think about that for a second. Negative b will be this number really close to negative infinity. Okay, so we have y is equal to 1 over negative b. So what would that one look like? It'd be like 1 over 10, 1 over negative 100, 1 over negative with lots and lots and lots of zeros, right? As many zeros as you can draw. We could do this all day. What's happening to the value of that fraction? Well, it's actually, we want to say that it's getting smaller And magnitude-wise it is. So this is where we get into this little sticky situation about how we describe these numbers. Sometimes I'll say a really big negative number. And what I mean by big negative number is that it has a big magnitude. And what does magnitude mean? It means it's distance from zero. Okay. This one has a bigger magnitude than this one because this one is really, really, really close to zero, right? Because that would be something like this. And this would just be this. So if we were to graph these numbers on a graph, right? If I'm trying to graph this one, so that would be, would be way, way, way out here at this number. Would be like right here, right above the x-axis. We probably wouldn't even be able to draw a point that's close enough to represent this distance, right? My pen is too thick. And this one would be more like at -10 would be more like here, -1/10. So if this were 1, this would be -1/10. Does everyone see what we're talking about here? Or actually, I should have done them negative because I lost my mind here. They should be here and here, right? Because they're actually negative values. So if this were -1, this would be -1/10, and this would be negative whatever this is, right? Really, 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 really close. So you can see here that this one has a bigger magnitude because if this is 0, he's farther away from 0. But I think of this one as a big negative number because he's so, this one as a big negative number to me would mean that he's way, way down here. So sometimes I say a big negative number to me means he has a big magnitude. So sometimes you'll catch me saying big negative number, but what I really mean is these numbers are actually smaller than these numbers up here. Okay. So we get into this like confusing way to describe it. Okay. So in other words, this number is actually bigger than this number because the numbers as we go this way get smaller. But this one is closer to 0. Do you see that? So he's way up here and he's way down here. So this one is closer to 0. So it has a smaller magnitude, if you want to describe it that way. Okay. And we said that these ones, what was happening, as I put these numbers that for x that are close to infinity, like over here, like 10, that put me here. And then they start to do this, right? They start to get really close to this line, this x, so that they're practically touching the line as we keep going out here, as we keep putting bigger and bigger x's in, like 10,000, a million, a trillion, a billion. We're going to get closer and closer to the x-axis. But here, if I put a positive number in, I'm always going to get a positive value. There's no way to get a 0 because the top can't be 0. And there's no way to get a negative, which means he's just going to keep getting closer and closer to the x-axis, but he's never actually going to reach the x-axis. And on this side, he's going to get closer and closer to the x-axis, but from underneath, so he's going to keep getting to be a bigger number, actually, right? A bigger number closer to 0 from underneath here. And we saw in the last video that we're actually getting closer and closer to this line also. We saw that this was the picture of that y is equal to 1 over x in the last video. Okay, so this is a horizontal asymptote. It's this horizontal line that the function is getting close to. In other words, all my function values are going to get close to 0 because these numbers, think about it, they're really, really small, right? If you had 1 over 800 million, trillion, billion, cajillion, you'd basically have nothing, right? And if you had 1 over negative 100 million, billion, jillion, cajillion, you'd basically also have nothing, right? The function values, as we get farther and farther out here, the function values, meaning the y values, are going to be basically 0. That's what creates the horizontal asymptote. As x gets really big, y is going to get just actually closer to 0. Not really big, really small. Okay? So let's look at another one. Another horizontal asymptote. You ready? So here's another one that we could have. All right. Now this guy, let's take a look. How did I say that we can kind of tell if it has a horizontal asymptote or see what the horizontal asymptote is, I said, well, let's imagine a really, really big number in for x, okay? So this would be like 2 times a really huge number over a really huge number plus 3. Now remember, this huge number is basically infinity, okay? B is basic infinity. Okay, let's think about this for 1 minute. Let's say that, you and I are walking down the street when we were allowed to walk down the street, right? And we have $1 in our pocket. And you see a $10 bill flapping around in the wind. It's being blown in the crazy wind that we're having, right? On a stormy day, you're walking down, it's wet. And you see a $10 bill blowing around in the street. You only have $1 to your name. What are you going to do? You're probably going to try to catch that $10 bill, right? You're going to at least give it a good effort. You're going to try to grab it a few times, right? Don't you agree? I would. So I see a $10 bill. I'm like, woo, $10. And I try to catch it, right? This is me. This is the $10 floating in the sky. So it's floating in the wind. So I'm going to try to catch it. I'm going to make a good effort at it. Now let's imagine that I have $3 million in my pocket because I'm just so rich. I'm that rich. And I see a $10 bill. It's raining. It's pouring. It's disgusting outside. Floating in the wind, $10 bill. I'm probably not going to make that big an effort to try to catch that. I'm going to make more of an effort to get to my car and stay dry, right? To me, this $10 is a lot when I only have $1. To me, $10 is a big difference. I want $10 if I only have $1 to my name. But if I'm someone who's walking around regularly with $3 million in my pocket, $10 doesn't mean anything to me. I'm not going to worry about $10. I'll be handing out $10 to people on the street for just to be a great person. So relative to what you have, $10 can be a lot or $10 can be basically meaningless. Now let's think about this for another second. Let's say that you have basically infinite number, money. You can make money. You have a money tree in your backyard. You grow money every day. If you have infinity, so your money tree plus $3, how much money do you have? You basically have infinity still. Does that make sense? Infinity plus another $3, who cares? But if I have $1 plus another $3, that would be a big deal. But we are talking about when x is really, really huge when we're talking about these horizontal asymptotes. So I'm imagining this is a really, really huge number. So I have 2 times infinity, right? 2 times infinity. Really, really big. Twice infinity on the top. And on the bottom, I have infinity plus a tiny amount. So I'm not even going to worry about this tiny amount. This tiny amount is basically, useless. Nobody cares about it. It's not worth my even thinking about. If I said I had an infinite number of, dollars to my name and someone handed me $3, I wouldn't say, oh, I have an infinite number and 3. I'd still say I have an infinite number. So relative to how big this B is, this 3 is kind of, he doesn't matter, right? He's a peon. Nobody cares about him. So infinity plus 3, I'm just ignoring this plus 3. And on the top, I have twice infinity. So this would be, like I have infinity and someone else has twice infinity, twice a really huge number. Well, they're always going to be a lot bigger than me. How much bigger? Twice bigger, right? So the way I think about this is I say I have 2b over b plus 3, but this plus 3 we're saying we don't care about. We're ignoring because he's too small to worry about. So I'm just ignoring him. So what would this fraction reduce to? 2b over b. Well, these infinities would cancel out, wouldn't they? Basically. And this would be a 2. So in other words, this fraction, if I put really, really huge numbers in for x, this fraction is actually going to get close to 2. And the funny thing is, the bigger the number that you choose, the less this 3 adds to it, and the closer the fraction actually gets to 2. Do it on your calculator if you want. Do 2 times 10 over 10 plus 3, and then do 2 times, keep doing it like we did before, and put these really big numbers in. And what you'll see is that this fraction, as you go, gets closer and closer into 2. If you keep putting a bigger and bigger number in for x, this fraction actually gets closer and closer to the number 2. At some point, your calculator might even tell you it's 2 because it's just so close to 2, it can't even tell the difference. So in this case, my horizontal asymptote, HA I'll put in for horizontal asymptote, is going to be y is equal to 2. This one's going to have a graph that as x gets really big, y gets closer and closer to 2. Okay? All right. Now there's one other thing that we could happen, and then I'll kind of sum up so you can kind of keep track of what I'm talking about. The last thing that could happen was something that looks like this. Y is equal to, so there's 3 scenarios. I mean, there's lots of different asymptotes. We can get a million different asymptotes, and I'll show you that in a second. But there's basically 3 scenarios that can happen. All right, the next one is something like this. Okay, now this one is a little bit different than the last one because now we have 3 times, let me just use infinity for a second, infinity squared over infinity plus 2. Okay, now remember, just like in the last one, this guy, infinity plus 2, I'm not going to say infinity plus 2, I'm going to ignore the plus 2. Okay, so what we end up having here is 3 over infinity squared over infinity. It's basically what this fraction is sort of equivalent to. Does that make sense? If we're talking about when x is really big, and that's what we're talking about when we're talking about horizontal asymptotes. And of course, what would this reduce to? Well, this would reduce to a 1, and this would reduce, and this would be 3 times infinity. So what number is that? Well, 3 times infinity, infinity. This is approaching infinity, right? It's getting close to infinity. It's a really big number. So for this one, as x gets really big, y actually gets really big. So this is no horizontal asymptote. And why? Because we said that x would have to be approaching a number. And infinity isn't a number. It's this idea, right? It's an idea. It's this list of numbers. So if the fraction is going to get close to infinity when x gets close to infinity, that's just end behavior. It's not an asymptote. It's not a horizontal asymptote. Okay? So how did I figure this out, and how do I sum this up? So let's take a look. There were a couple things that could happen. I could have something that looks like this. Something like this, where if I think about it as infinity, right? So I'm thinking about putting in a really big number in for x. So how do I find horizontal asymptotes? I let x approach infinity. So I pretend x is really huge, okay? So what happens here? This guy is useless, right? So then eliminate everybody that's kind of just hanging out. And anybody that's smaller than infinity is just puny. We don't care about him. He's like immortal, mortal. No, you don't care about them, right? Superhero, regular guy. We don't care about the regular guy, right? So what's happening here is I'm pretending that this 1 doesn't exist because as I get really big, as I start to increase in my size, nobody cares about, oh, I don't know where this 2 came from. Sorry. I just added that 2 for fun. As I get really big in size, $1 doesn't mean much to me. So as I increase my bank account, nobody cares about $1. So I'm just ignoring him. And then what happens? We reduce, right? So this infinity and this infinity. And then what do I have? I have 2 over infinity. So basically the same. They don't equal each other, but they kind of have the similar value, right? When x is really huge. Well, how big is this fraction? A fraction with a big bottom has small size, has small value, right? So if this is a really big number on the bottom, this fraction has a really small value. In other words, y is approaching 0. So my horizontal asymptote is y is equal to 0. Make sense? So when you look at it this way, you think about a really huge number. Ignore everybody that doesn't matter that much. So all of these little extra guys on the end, we're just going to ignore them. And we're just going to look at this leading guy that has our infinities in it. And once you reduce it, if the bottom is really big and the top is not very big, then that fraction is going to get really small, in other words, close to 0, and you'll have a horizontal asymptote of y is equal to 0. If you have something that looks like this, well, this one's a little bit different, because what's going to happen here is I'm going to put in infinity for the numbers, right? So we're going to have 2 infinity squared plus 3 times infinity plus 1 over 3 infinity squared plus infinity minus 3. And then I'm going to eliminate the people that don't matter that much to me. So I'm being really harsh here, yeah? And I'm getting rid of everybody that's, kind of not adding that much weight to me. And how big is infinity compared to infinity times infinity? Not very big. So we're only looking at these leading terms, the biggest term. And these other guys, I'm going to ignore them because they're kind of worthless to me. So too small to worry about. Right? So what do we have left here? We have this fraction. So now we're looking at a fraction that looks like this. And what happens here? Now I can reduce these infinities, right? And so this is a fraction that's really gets close to the value of 2 over 3 when I eliminate everything that kind of doesn't matter that much. So my horizontal asymptote here is going to be y is equal to 2/3. Okay, so I'm doing that same process every single time, and I'm just looking to see what kind of fraction do I end up with. Now the last thing that could happen is something like this. Okay, so again, I'm going to put in my infinities and kind of look at what do I have here. So I have 2 infinity squared plus 3 infinity, 3 infinity plus 1. And again, I'm going to just eliminate everybody that doesn't matter to me. So at the top, he's much smaller than this one, so I don't care about him. And 1 is much smaller than this one, so I don't care about him. So again, I'm really only looking at this first stuff, the leading thing. And then what happens, I can reduce these infinities, right? And this will be 2 infinity over 3. So what number is that really? That's really like y is approaching infinity, which means no horizontal asymptote, because y has to get close to a number. Because y does not approach a number. Okay? Because he doesn't approach a number. So there's 3 scenarios that can happen. You can have a fraction where the bottom gets really big and you go towards 0. You could have a fraction where they're kind of the same size on top and bottom, and so the fraction ends up being the leading coefficient. Or you can have one that has no horizontal asymptote. So some people say, they kind of sum it up in this way. They say, so this first scenario, if you wanted to sum it up, if degree on bottom is bigger than top, your horizontal asymptote is going to be y is equal to 0. This fraction is going to get close to 0. See how the degree on top is bigger than the degree on the bottom? And that was true here. The degree on top of this one is 0, and the degree on the bottom is 1. And what do I mean by degree? I mean the size of the exponent. Okay? So if the degree is bigger on top, then you're going to get this. That's the situation here. You're going to get y is equal to 0, because that fraction is going to have a value closer and closer to 0. The second one is if degree on top is same as on bottom, then you're going to get an asymptote that's y is equal to the leading coefficient. So what was the leading coefficient on this fraction? It was 2/3. And remember I said my asymptote was y is equal to 2/3. So what happens here is you ignore everybody that's not the leading terms, right? And then these x's kind of cancel out, right? And you're left with a fraction that's just the leading coefficient. Okay? So that's the second thing that can happen. And what's the last thing that can happen? Is this situation. If the degree on bottom is smaller than top, well, what ends up happening is you do the same thing. You just ignore everybody that's not the leading terms. The x's cancel, but you're left with an x on top. So you're left with like an infinity on the top and just a number on the bottom. Well, a fraction that has a really big top has a really high value. So that means that that is going towards infinity, which means no horizontal asymptote. And those are really the only three things that can happen with these horizontal asymptotes. You can get one that's equal to 0, one that's equal to this leading coefficient, or one that doesn't exist. And we will talk about what it means. You know, there are other kinds of asymptotes that you can have, but these are your three choices when they talk about horizontal asymptotes. Okay? Alrighty.